Welcome. This video analyzes resistor inductor RL circuits with constant value voltage sources and current sources. By applying basic knowledge of inductors, sources, and resistors, the goal of this video lesson is to identify, by inspection, voltages and currents in all four of these RL circuit topologies. At DC, zero frequency, an inductor looks like a short circuit, like an ideal schematic wire. The current from an ideal DC current source with a constant value of current can flow in a loop through an inductor, just like current can flow in a loop through an ideal wire, shown on the right. Notice how there is no resistor and no voltage drop in the circuit. While the current has a definite value, the voltage is indeterminate.
For more technical background and insight on inductors, current sources, and RL transient circuits, please see this book, First and Second Order Circuits and Equations.
Now we have the first of the four RL topologies to analyze. This parallel RL circuit driven by a DC current source. Compared to the previous current source and inductor circuit, we have now added a resistor in parallel.
Now, with the resistor added, what currents and voltages do we get in this new circuit?
We actually get the same current behavior that we got previously without the resistor. The entire current goes through the inductor just as before. No current goes through the resistor. Modeling of the inductor as a short circuit for DC analysis is shown in the equivalent circuit on the right. The current won't go through the resistor when the current can much more easily go around the resistor. SPICE simulation of this parallel RL circuit, driven by a DC current source, matches expectation that the current goes around the resistor. The current through the source and the current through the inductor are the same, 1 amp. Besides the ground node, the only other node, labeled with RL, has a voltage that is effectively zero. One more way to show the parallel RL circuit DC behavior is this transient QSPICE simulation. Because the current is constant valued, the currents don't change with time over the 3 microsecond simulation. We see clearly how the red signal at the top of the graph shows 1 amp inductor current, I of L1. The lavender signal at the bottom shows 0 resistor current, I of R1. These transient values match the DC values for current from the previous DC operating point simulation. For the second of the four RL topologies to analyze, we replace the current source with a voltage source, giving us a voltage source in parallel with a resistor and inductor.
Whoa! This circuit looks like a problem right away.
That's right. There is now an independent voltage source placed across the inductor, which is an ideal wire, a short circuit at DC, as indicated in the equivalent circuit. The voltage source specifies a voltage difference between the top and bottom nodes. By contrast, the inductor at DC specifies no voltage difference at all between those same two nodes. The circuit has no solution and simulation will fail. There are not two electrically distinct nodes in the circuit. Because the current will go around the resistor, we can make an even simpler equivalent circuit on the far right, with a short-circuited voltage and no resistor at all.
Question: what does short-circuiting a voltage source look like in the real world?
The answer is not pretty. Short-circuiting a voltage source might look like two batteries being short-circuited by a wire. This will drain the batteries, and it might cause heat, sparks, melting, or even an explosion in some cases. Now we have the third of the four RL topologies to analyze: a series RL circuit driven by a voltage source. The inductor acts like a short circuit at DC, effectively removing the inductor from the DC circuit. The circuit in the middle and the circuit on the right are equivalent circuits to the series RL circuit on the left. We see in the drawings on the right, all the voltage from the voltage source drops across the resistor, setting up a current in the loop of V over R equals I, Ohm's law. Here is a quick simulation of the series RL circuit driven by a DC voltage source. The simulation type is DC operating point. PR1 on the schematic is a current meter, measuring inductor current at 0.05 amps, 50 milliamps. The resistor current, rescur, is calculated using Ohm's law in two different equations under the equations block.
Quiz question: if we increase the inductance L1 by an order of magnitude, how will the increased inductance affect the simulation results?
The answer is not at all. Changing the inductance does not change the simulation results. At DC, the inductor acts like a wire, a short circuit, so the nominal value of the ideal inductance does not matter. 100 microhenries of ideal inductance in this simulation gives us the same DC current as the 10 microhenries of ideal inductance in the previous simulation. Now we have the last of the four RL topologies to analyze: a series RL circuit driven by a constant current source. Modeling DC by shorting the inductor, we get these two equivalent circuits for the original RL topology on the left. We are given the current value I from the independent current source specification. We can calculate the voltage across the resistor from Ohm's law, V equals I times R. The voltage across the source and the resistor equals the current times the resistance value. Summarizing, when the inductor is modeled as a short circuit at DC, we can remove the inductor from the circuit and replace it with a short circuit or an ideal wire. We can use Ohm's law to calculate voltages and currents.
Thank you for watching and learning with us.